This video will cover cross-validation using the modelr package. By the end of this video, you should understand how to perform k-fold cross-validation, how to use the features of the modelr package to simplify performing k-fold cross-validation, and how to train, evaluate, and compute average loss for many models using k-fold cross-validation. The R code and data used in this video are available on the Learning Management System. You'll need the PJM elec weather daily _train.rds data file. Before we get to model evaluation using cross-validation, we're going to do it the wrong way, which is evaluating in sample. So to get started with that, let's evaluate two candidate models in R. We'll load the PJM elec weather daily _train.rds dataset, and we're going to define two models. In model 1, our label demand will be a function of high temperature in New York, the high temperature in DC, and the high temperature in Chicago, and all of their interactions. In model 2, our label demand will be a function of those same variables, but instead of just their first order interactions, I'll also include interactions up to the 4th degree polynomial of each feature. We're going to train these models and compare their in-sample root mean square error. So let's get started in R. I'm going to load that data file and all the libraries that I'll need. This will include the modelr library. Next, because I'm going to use these formulas several times, I'm going to save each of them in a variable. I'll call the first one formula A and the second one formula B. Now that I've saved these in variables, I can just use the variable instead of typing out the formula in my linear models. What I'd like to do now is train each of these models on my data and then compute the value of the loss function, root mean square error, in sample. I'm going to do that here. Looking at my output in R, you can see that the root mean square error of model A was 151,238, and the root mean square error of model B was 140,762. If we were using this in-sample fit to evaluate our models, the root mean square error for model B is smaller, and so we would prefer model B over model A. But do we really think model B is the better model? Model B has a lot of parameters, and we evaluated the fit in sample. And as we've seen in previous videos, this can lead to overfitting. Using out-of-sample evaluation is one way to protect against overfitting, and we've seen that k-fold cross-validation is one way that we can perform this out-of-sample evaluation. So let's recall the steps that are in k-fold cross-validation. First, you're going to randomly divide your data into k-folds or subsets. You're going to train your data using k-1 of those folds, and then you're going to test your model on the remaining fold. From this test, you're going to save the value of the loss function. You'll repeat this process for every combination of training and test folds. And we're going to prefer models that have the lowest value of the average loss across all of those folds. So we'd like to do k-fold cross-validation in R. Step 1 is to randomly divide our data. How can we do that? R has a useful function called the sample function to help us here. What sample does is it will randomly choose between values in a list of values we provide. So in the prototype code that I have here, I'm taking my electricity data tibble, I'll pipe it to the mutate verb, and I'll generate a variable called fold ID. Using the sample function, it will take either values 0 or 1. I use the end function to tell R how many times I'd like to sample, which is the number of observations in my data set, and I set the replace option equal to true, saying that I can use the values 0 and 1 more than once. It's important to emphasize that randomness and reproducibility are inherently incompatible. We'd like to randomly divide our data, but at the same time, if I give someone else my R code, I'd like them to be able to get the exact same results as me, which means they would need to divide the data the exact same way. We can get around this by setting the random number seed in R. You can do that using the set.seed function. It takes a number as an argument. You can pick any number you'd like. Here I'm using 1, 2, 3, 4, 5. If you set the random number seed to a specific number, R will always choose the exact same sequence of random numbers. This means if you share your random number seed with someone, they can divide the data the exact same way because they'll produce the exact same sequence of random numbers that you did when you divided your data. So let's do two-fold cross-validation in R. I'll start by setting the random number seed. Here I'm going to use a longer number, 1, 2, 3, 4, 5, 6, 7, 8, 9. Next, I'm going to randomly divide my data using the sample function. Just like in the slides, this function assigns a value of 0 or 1 to the variable fold ID randomly for each observation. We can take a look at that in the console. You can see over at the right, there's a new column called fold ID, which is either 0 or 1. This hasn't yet divided our data. What we'd like to do is create two tibbles, one where the fold ID is equal to 1, and the other where the fold ID is equal to 0. You can see that I have two statements. The first one filters my data to where fold ID is equal to 0, stores it in the tibble elect.0, and I do the same thing when fold ID is equal to 1, storing the data in elect.1. Looking over the Environment Explorer, I now have two different tibbles. The first elect.0 has 947 observations. The second elect.1 has 875. They have a different number of observations because I generated the zeros and ones randomly, and we wouldn't expect them to be precisely equal. So let's go back to my code. Remember, the next step in k-fold cross-validation is to train our model on one fold of the data. Here I'm going to do that. I'll train model A on fold 0. The next step in k-fold cross-validation is to calculate the value of the loss function on the fold we didn't use to train the data. That's what I do in the next part. I calculate the root mean squared error using model A, but on the data in the elect.1 tibble. I'll run that and print it out, and you can see the value of the out-of-sample loss is 149,993. Going back to my code, now we can go through the exact same process for the other fold. We'll train our model on the data in elect.1 and then compute the value of the loss function on elect.0. Running that and looking at my output, you can see the value of the loss function on that fold was 154,154. The final step in k-fold cross-validation is to calculate the average of each out-of-sample loss that we calculated. I do that here, computing RMSE for model A as the average of the loss from each of the iterations above. Running that and looking at my output, you can see the average loss across each iteration was 152,073. The whole point of k-fold cross-validation is to compare models. We'd like to compare model A to model B, so I'm going to go through the exact same process with model B. I'll train model B on fold 0 and compute the RMSE on fold 1. Then I'll train the model on fold 1 and compute its RMSE on fold 0. Lastly, I'll take the average of the loss computed out of sample on each fold, and that will be my two-fold cross-validation RMSE for model B. Let's run all of that. You can see here that my cross-validated root mean square error is 586,499. Let's compare that to the root mean square error we got from model A. I'll just print out both here. You can see that the root mean square error here for model A is much smaller than model B. This is in stark contrast to what we saw when we evaluated the models in sample, and this is really strong evidence that the model in model B is overfit on the data. This would make me very worried that I would get very poor forecasts if I was using model B to predict future electricity demand. These are all the steps that you would need to go through to two-fold cross-validate two models in R. That's a lot of typing and a lot of code. Fortunately, the modelr package makes it very easy for us to perform k-fold cross-validation on many models. The most valuable part of this package is the cross-v k-fold function. It takes two arguments. The first argument is a tibble of data. You can feed that in with the pipe if you would like. The second argument is k equals, where k is the number of folds that you would like to use in your cross-validation procedure. Before we use cross-v k-fold for cross-validation, I'd actually just like to take a look at it to see how it works. So what we're going to do is take our electricity data and prepare a cross-validation tibble using the cross-v k-fold function. You can see here I have R code identical to my slides. I'm feeding the elect tibble into the cross-v k-fold function, and I'm setting k equal to 10, saying I would like 10 cross-validation folds. I'm going to run that and print out the result. Looking in the console, you can see we get some very cryptic output, including a train column, a test column, and an ID column. You might be asking yourself, what did R do here? And the correct answer, having never seen this before, is probably, I don't know. So what did happen here? Cross-v k-fold creates a new tibble that has k rows. Each row has a train and a test column. Each of the values in these columns is actually its own tibble of data. That tibble contains the same variables as your original data, but the data were divided into k folds. The tibble in the train column has k minus 1 folds of the data, and the tibble in the test column has the other fold. So you might wonder why these tibbles packed inside of tibbles are useful. Each row of this new tibble has everything you need to do cross-validation for one iteration of k-fold cross-validation. There's some other R magic that I'll show you in just a minute that allows you to train models and compute the value of the loss function using very familiar dplyr syntax. The nice thing about this is dplyr is going to automatically perform each of these steps on every fold, so you don't have to do it manually 10 times. How is this going to work in practice? Remember our general outline for k-fold cross-validation? We'll randomly divide our data into k folds, and then for each model that we're considering, we're going to choose k minus 1 folds as training data and train the model. We'll test the model on the remaining folds. We'll save the value of the loss function from that iteration, and then we'll repeat that process for every combination of folds. In the end, we'll prefer models with the lowest average value of the loss function. How are you going to do this in modelr? We'll divide our data using cross-v-k-fold. For each model that we're considering, we'll train all the models on the training column. We'll test all of the models on the test column. And then we'll summarize our new tibble to compute the average loss for each of those models. Just like before, we'll prefer the model with the lower value of the average loss function. Training all of our models requires one additional R function that you might not be familiar with. What we'd like to do is use the data in each of the train observations to train our model. To do this, we're going to need the map function. What the map function does is run some piece of arbitrary R code for every observation in your data. Here, what this might look like is you would use the map function. You tell it you would like to use the train column as the next argument. You use the tilde, and then some piece of R code that you would like to run. The period is a shortcut for that training data that you provide as the first argument. We can put this map function inside of a mutate verb, and it will generate a new column for us that contains each trained model. So let's go through and use this on some of our data. We're going to train models on this cross-validation tibble, elect.cv, and then we'll look at the resulting tibble. Looking at my R code, I take that elect.cv tibble, again I pipe it to the mutate verb. I'm going to create a new column, cv.model.a. It's going to contain the trained models for each iteration using formula A. I use the map function. I tell it I would like to use the train column. I type a tilde, and then the R code that I would like it to execute for each value. I'll save that result as elect.cv.1. Let's run that and look at the output. You can see that my cross-validation tibble now has a new column, cv.model.a. The value in each cell is the result of that lm function. Now that we've trained our models, we'd actually like to compute the loss function out of sample. Remember, the test column contains our test data for each iteration of k-fold cross-validation. To compute the value of that loss function, we're going to need another R function, which is map2double. This is very similar to the map function, but instead it allows us to provide two arguments. The way this is going to work is we'll use the map2double function. We'll feed in a model in the first argument. We'll tell it we would like to use the test data in the second argument. And then in the third argument, we'll give it the name of the loss function we'd like to use. Again, we can do all of this in a mutate verb, and it will create new values in our tibble that contain the value of the loss function for that iteration. So let's take a look at my code here. I take that electcv.1 tibble. I pipe it to the mutate verb. I'm going to create a new column, cv.rmse.a. I use the map2double function. In the first argument, I provide my trained models. In the second argument, I provide the test data that I'd like to use. And in the third argument, the loss function that I'd like to use, RMSE. I'll run all that and look at the output. You can see now there's an additional column in my tibble that has the value of the loss function for each cross-validation iteration. I've calculated the value of the loss function for each iteration. That's stored in a very familiar column with the double column data type. But what I'm really interested in is the average across all of these iterations. How could I compute that? By this point, we should be familiar with summarizing our data tibbles. You can just use the dplyr verb summarize to calculate the average value of this column. So looking at my code, that's exactly what I do here. I take that elect.cv.2 tibble, I pipe it to the summarize verb, and I calculate the average loss for model A as the average of all those individual loss functions from each cross-validation iteration. Let's run that code. And you can see I get a value of 151,904. This is different from what I calculated with two-fold cross-validation. First, because there are more folds, and second, because I randomly divided my data. So you wouldn't expect the folds to be divided the exact same way each time, unless I had set the random number seed ahead of time. So hopefully at this point, you see how using cross-v-k-fold might be faster than doing cross-validation by hand. But there are still ways that we can condense this into much easier to read and faster to type code. We can combine all, or at least most of these steps together using dplyr pipes. So looking at my code here, this is precisely what we do. I'm going to compute the loss using k-fold cross-validation for both model A and model B and compare them to each other. I'll start out by setting the random number seed, so anyone else who runs this code should get the exact same result as me. Then I'll take my electricity data tibble, I'll pipe it to cross-v-k-fold, setting the number of folds equal to 10. Then I'm going to cross-validate all of my models inside of the mutate verb, first model A, then model B. After training all of the models, I'll evaluate them, first for model A, then for model B. I'll save this result to elect.cv. And finally, I don't care about the individual losses from each cross-validation iteration. Instead, I care about the average. So I'm going to use the summarize verb and compute the average loss for both model A and model B. If I run all of this code, looking at my output, you can see the average loss for model A is 151,706, and the average loss for model B is 193,259. The average loss for model A is lower So we would tend to prefer model A over model B because we think it would have more accurate predictions out of sample.